Okay, so in this video, we're going to go over an introduction to electricity and electric circuits and some of the terminology that we'll use and the concepts that we'll use to think about electricity flowing in circuits. So at the top, we have an open circuit, and at the bottom, we have a closed circuit. And most of you have already shown that you understand that when the circuit is open, the light bulb will not light, and when we have a closed circuit, then we would expect the light bulb to light. Okay, let's try to talk about why that is. Hopefully by the end of this video, we'll have some understanding of that. So if you were to zoom in to the atomic level and see what's going on inside the wire, you would see that inside of the wire, which is going to be made of metal, like copper, or something that's a very good conductor, there are going to be all these things called electrons, which are negatively charged and which are moving around freely. And so obviously this is a static picture, but you can think of the electrons as randomly moving around within this wire. So the one key idea to get across, just to have a more accurate understanding of how this works, is that in the wire, the wire is already loaded up with lots of free moving electrons. So the wire contains many free moving electrons. Now, they're not all moving in one direction, and that's why it's not called an electric current or a flow of electrons, and that's part of the reason why the light bulb isn't lighting up. The electrons are moving in random directions because right now there's no voltage being applied to the circuit because it's open. But the wire contains lots of electrons right at the start. Okay, then what happens when we close it is that the battery provides something called a voltage. And the best way to think about a voltage, I think, or one of the best ways to think about it, is that a voltage provides like a push force. It's a push force on the electrons. So there's going to be a push in this direction on the charges in this circuit. Now, because the electrons are really, really packed together, when you start to push on the electrons, this electron here is going to bump into the electron in front of it, and it's going to bump into the electron in front of it, and that's going to bump into the electron in front of it. And so the electrons start to bump into each other and push one another down in this direction. That effect of the electrons bumping into each other is pretty much instantaneous. It's so fast that it's basically instantaneous. So the electrons are moving, and they are bumping into each other, like so. And when they bump into each other, they are transferring energy down the wire. So there's an energy transfer happening in the direction in which the electrons are moving. Okay. But actually, individual electrons are moving very, very slowly. So because this electron is going to bump into something in front of it, that's going to cause it to actually not move very quickly. So the actual electron drift, they call it, which is how quickly does a single electron actually move through this wire, is actually surprisingly slow. So the electron drift is around 1 meter per hour. So it actually takes an individual electron about an hour to travel through 1 meter of wire under sort of normal conditions, as a rough approximation. But the energy transfer, once you connect these things, we know that the light bulb turns on almost immediately. And that's because the electrons are bouncing into each other very quickly, and that electron therefore moves through, the energy moves through all those bumping electrons very quickly and is used by the light bulb. So the energy transfer is very fast, and that's between electrons, so they're bumping into each other. Think of that as passing the electron on from one electron to the next. And all the electrons start moving at the same time. So because that push is felt essentially instantaneously, when the push happens at this end, these electrons start moving, then they get pushed by the ones behind them. These electrons start moving, these electrons start moving, these electrons start moving. So the electrons are moving pretty much all at the same time, and that energy transfer is happening basically instantaneously, even though the individual electrons don't move very quickly. Okay, so when we have this closed loop we know that the light bulb will light, and that's because now there's this flow of electrons, which we call an electric current. So the current is equal to the flow of electrons. So the voltage is the push, and the current is the flow. If we increase the push, we should get more electrons flowing. And if we decrease the voltage, we decrease the push, we'll get less electrons flowing. So voltage and current have a direct relationship with one another. Okay, now what's happening inside the battery? Why do the electrons move when we connect the wires, the two different ends, to the two different ends of the battery? So a battery actually works with chemicals. It has chemical energy in it. So there are chemicals in here that have stored energy. These chemicals want to react with each other. They will react with each other if given the chance. So an example, this isn't really what's inside of a typical battery, but it is a similar kind of reaction that could work inside of a battery. So if you take the element zinc and you mix it with copper ions, copper 2+ ions, a reaction will occur. It happens instantly, and you see electrons. You don't actually see the electrons, of course, but you start to see a chemical change. And what you see happen is that the zinc starts to fall apart. The zinc turns into zinc ions, and the copper ions gain those electrons and turn into copper metal. So if you take a piece of zinc, stick it into a copper 2+ ions, you will see copper metal forming instantly. In real time, you will see this brownish metal start to form. And that's because zinc is more reactive than copper. So we say that zinc has high potential energy and copper has low potential energy. And the electrons, just like things tend to fall from higher altitude to lower altitude, electrons tend to fall from higher potential energy to lower potential energy. So the electrons on zinc have sort of a high potential energy. And if given the chance, those electrons will flow to copper 2+ ions. The copper 2+ will turn into copper, and the zinc will turn into zinc 2+. Now this is way beyond what we need to know in this unit. This is really a DP chemistry topic, but just wanted to try to give a little more explanation of what's going on here. So the electrons lose their energy as this reaction takes place. So the electrons go from a high energy state to a low energy state. So there is a difference in potential energy between zinc and copper. So we call this a potential difference. The electrons on zinc have a different amount of energy from when they're on copper. And so there's a difference between where they start and where they end. And that is a voltage. When there's a difference in potential energy for electrons, that creates a voltage, that creates a push force. So in a battery, the difference, you got these chemicals in here, is that those chemicals can't touch in a battery. So there's a barrier between them. So if I take away this writing, in between those two chemical reactants is a barrier. So they can't touch each other, and therefore the electrons can't flow. But if you attach them with a wire, if I take a wire and I connect the copper ions and the zinc, then, sorry, what is this? Got it. Okay. If I connect them with a wire, then that electron transfer, the zinc can now transfer electrons to the copper 2+. How does it do that? Well, the electrons have to travel through the wire to do that, which is what creates the flow of electrons through the wire. So the copper ions are like pulling on these electrons. So there's a pull on the electrons from the copper ions, and there's a push on the electrons from the zinc, and that creates this push force through the wire. So because the electrons want to go from high potential energy to low potential energy, they want to go from the zinc to the copper 2+ ions. They will naturally do that if given the chance. If you can connect those two chemicals with a conductor, with a wire, then the electrons will flow in that direction and cause that chemical reaction to happen. So inside a battery, you have copper 2+ turning to copper, and you have zinc turning to zinc 2+. So you have the same chemical reaction that I was describing before is actually happening inside the battery, and it's causing a flow of electrons. If you just hook a battery up like this, all the energy of this reaction will get released as heat. And so the battery will get really, really hot, and it can be quite dangerous. So instead, if you stick a light bulb in here, then as the electrons are going through the light bulb, like this, they actually lose the energy in the light bulb instead. And so the drop in energy happens across the light bulb, and we get light happening. And then the electrons don't get used up. The electrons continue to push along on each other and cause a drift in this general direction. And there still is this same reaction happening, but the battery doesn't heat up. The energy gets used by the light bulb. If you want to recharge a battery, you just have to hook it up to electricity. And if you want to recharge it, you have to push the electrons in the other direction. So if you want to recharge a battery, you're trying to reverse the chemical reaction. So you have to force the electrons back this way, and you turn the copper back into the copper 2+, and you turn the zinc 2+ back into the zinc, and you reform the original chemicals. So recharging a battery is actually reversing a chemical reaction so that you get back to your starting chemicals, so that the next time you use the battery, you have chemicals inside the battery that can react. So a battery is not just like a big holding container of electrons. A battery contains chemicals, and when you connect them in your device, the chemical reaction is what creates that force on the electrons, and it pushes and pulls the electrons through the electric circuit. Okay, so we have voltage is going to be our way of describing how strong a force there is on the electrons, how much energy and force there is on the electrons. We describe that in volts. And the flow of electrons through the circuit we call the current, and we describe that in amps or in amperes. The flow will only happen when we have a closed circuit, because that's the only way that the electrons actually feel that push and pull force. Unless the zinc, in this example, the zinc and the copper 2+ are connected, then there's no pull on these electrons. There's nothing pushing or pulling them. So we have to connect to the high and the low potential energy sides of the battery to create the push and pull on the electrons.